That does seem to be correct. We have 1 times 10 to the 6 centimeters cubed is equal to 1 meter cubed, right? So we can throw that right over there as well. We'll put in our units, and then we will pretty much be done. Let me erase this just for a moment. So let's see, before we calculate our final answer, we have kilograms canceled out with kilograms. We have now in the version of grams that we want. We also have meters cubed canceled out with meters cubed, giving us the units we want. So happily we've done what has been asked. The hardest part now is just doing the math. So we have 1.5 times 10 to the 5 times 1,000, or 1 times 10 to the 1, 2, 3. 1 times 10 to the 3. And then we're going to divide that by 1 times 10 to the 6. So the math isn't so bad here, right? 1.5 times 1 divided by 1, that will be 1.5 as well. And then we also have, right, 5 plus 3, so that's going to be the same as times 10 to the 8, divided by 10 to the 6th. And if we remember when we're working with exponents, we will just subtract these with division. And so this will be equal times 10 to the 2. And so our final answer in scientific notation, with 3 significant digits, is 1.50 times 10 to the 2, though on the exam I also accepted 150 grams per centimeters cubed as a very proper answer as well. So again, the biggest mistake might have been caught up here when we're confused between cubing just the units or cubing everything in this case. And at the end of the day, there isn't even much math going on, right? It's just sort of converting units. Okay, so we're doing well going through those exam questions. Let's now look at questions 5 and 6. And then we will move on to chapter 2, which you're welcome to skip ahead if you need. Okay, so for question 5, we were talking about atomic structure, and there were 3 questions we asked. First, we asked, for the proton, is the mass equal to the mass of the electron? And we know that not to be the case, right? We know that the proton is going to be relatively large or massive compared to that electron, around 1,800 times as large if we set the electron mass to 1, so much, much larger. So they are not equal, and so that would have been false. Now we look at the charge between the two, and if I'm being particular, which as a chemist I have to be, we know that the values of these charges are going to be the same, the magnitude, right? They are both 1.602 times 10 to the negative 19 coulombs, that elementary charge maybe you've seen. But we do know that the proton is positive and the electron is negative, and thus negative 1.6 times 10 to the negative 19 is not equal to positive 1.6 times 10 to the 19. The magnitudes are the same, right? The size is the same, that extensive measure, but essentially the value is different there. So this would have been false as well. In terms of the structure of the atoms that we're working with, we have our protons and neutrons in the center. And we have in this cloud on the outside essentially all of our electrons. So yes, protons and neutrons do reside in the atom, or in the nucleus, I should say. That is true. And then as we can even see in this diagram, it is true that most of our atoms are empty space. And so again, if you're ever poking your younger sibling and they say, "Stop touching me," you can say, "I'm not touching you because there's mostly empty space between us when I am." Silly and pedantic, but it works nevertheless, especially when you're torturing your siblings. Okay, so let's round this out for the day by looking at question number 6. And so question number 6 looked at, again, not actual elements, but just how we represent them. And so briefly, let's review that if we have an atomic symbol represented by a large letter, oh gosh, you can't really see that on there, can you? Is that any better? Yeah, a little better. If you have a symbol and you have 2 numbers, we have The first number is going to be the mass number on top. And we find, right, this might be a little different on some periodic tables, but when we represent them in words, in papers, this is how it will be. This is going to be the sum of the protons and neutrons. And so in this instance, these are all the heavy things, right? Those electrons are so light, 3 orders of magnitude lighter, they won't actually impact what we have here. And then on the bottom, we have the atomic number, which again is kind of similar to this symbol, right? They both mean a certain number of protons. So now we can go back to our specific fake example of vibranium, in case you're a Marvel fan. Now we do actually have an element that is at 99, so this maybe isn't the best example, but it'll suit us fine today. And so for our first question of how many protons there are 99 protons. For the question of how many neutrons there are, we're going to take this total mass and subtract the number of protons to get the number of neutrons. And so we can see here it is 16. And then last but not least, if an atom of Vi is going to have a positive charge, we know that there's now an imbalance in the number of protons and electrons. And so if one electron was taken away, we know that it's going to have one less than the number of protons. So if there are 99 electrons to start, and you take one away, we will have a total of 98 electrons to sort of almost balance out that nucleus that we have with 99 protons, I should say. So those were some of the more challenging questions from the exam. And if they're still not making too much sense, please feel free to come to me. Happy to sort of go through other examples with you. But I would definitely suggest in the back of the book some of those problems just to get a sense of how to do some of that math and what those tricky ones actually look like. Okay, so now we are going to shift into Chapter 2. And there are a wide variety of topics covered in this chapter. For example, how to name different compounds, the periodic table, the types of categories in the periodic table, which we covered and probably is a bit of review for some of you. I'm going to look at some of the more challenging things, or things I think are worthy of a challenge. So let me actually look at the questions that I wanted to do. Let's start with question 2.67 from the book, and we'll go through those as we need. Okay, so we have a compound, a chromium compound, right? Cr for chromium, and then acetate, it looks like, C2H3O3, no, O2, and then 3, right? We need to make it a little hard. So that means that for every chromium atom, we have 3 of these different species, also known as the acetate. Circling around it. We'll find that metals, especially transition metals, really like to have lots of organic things surrounding them. That's how a lot of our proteins work, for example. And so we want to know how many of each element are in here. So the first thing I would do, let me write this out, how many of each element. So we are going to list them. We have our chromium, we have our carbon, we have our hydrogen, and we have our oxygen, right? Only 3, well, there's technically 4 letters, but this is one symbol, and then we have 3 other letters. And so we can see, for example, that we only have one chromium, right? There's no subscript here, and there's nothing multiplying it. This 3 is going to refer to what's in our brackets or our parentheses. So we are going to have one chromium. We know that in each of these ligands, or these species connected to the chromium, of which there are 3, we have 2 carbons. So we are going to have 2 carbons per ligand times 3 ligands, or 6. So to give you a sense of kind of what I'm talking about, if this is our chromium atom, we're going to have 3 things hanging off of it, and each of them is going to be C2H3O2. So there are 3 of these in total. So looking back at the H, we know we have 3 per ligand, and then we also have 3 total, so we have 9. And then lastly, with oxygen, similar to the math for carbon, we have 2 times 3 is going to be equal to 6 total. So some sorts of questions I could ask: what are the total number of atoms in this molecule? Well, we have, let's see, 15 plus 6 is 21, plus 1 is 22, so 22 total atoms. I could ask you how many metallic atoms, that would just be the one chromium. How many nonmetals in this compound? You have, 21 total. Other things, that's about really all that you can ask, I guess. Though I also guess you're going to be working towards, in future chapters, the molecular formula. So that's going to not be this thing that represents all of them, but just has each of the elements written once. And so you could also, for example, do Cr and then C6H9O6. But there's a lot less information in this sort of molecular formula than this formula, which hints at the structure, right? It hints that there are 3 separate collections of those carbon, hydrogen, and oxygen atoms. Okay, so let's move on to our next question. And let me see what that was. Question 2.109. And for this one, we're going to be writing the formulas for the following named compounds. So I'll write a couple names up, and we will write out our formulas. Sodium, hydrogen, monophosphate. Sounds like something you might find on the back of a commercial fruit product, for example. We have lithium selenide. We also have iron 3 oxide. And let's do antimony pentafluoride. Okay, so 4 very different names, right? We have a very long name with 3 components. We have a simple 2-component name. We have a transition metal compound, iron here, with its oxidation state, which we'll come to describe. And then lastly, something with a prefix indicating how many of these that we have, though I guess we see another prefix up here too. So the first thing that I like to do with names is just to put the elements on top of what the name is talking about so that you know you need each of those before you're done. So we can take sodium, hydrogen, and then phosphate doesn't refer just to phosphorus. This is one of those polyatomic anions or ions. And so hopefully I give those to you, but getting more familiar with common ones like phosphate and sulfate will definitely help you out, probably in a variety of courses. So we know, for example, that we have PO4 3-. So again, you're pulling that either from the back of your brain or from a reference table. Similar for lithium and selenium, we have just the compounds themselves. For iron, we're given the oxidation state, so we're going to be able to balance the stoichiometry or the number of these based on the states of these things. So right, it doesn't match up perfectly 3-2, so we'll do a little math in just a moment. And then lastly, gosh, antimony, I want to say that's SB. I wish I had checked this before. I think it is. And then the pentafluoride, so you can guess not only is it fluorine, but there's going to be 5 of them as well, right? And so the nice thing is because there's no other signifier, we're going to imagine that there are one of these. So now that we have all of the components, let's begin to put some of these together. So let's start up top. Here we know we have a charge of 3-. Hydrogens are always, at least in this course, going to be +1, and sodium is +1 as well, but you can notice, for example, that I wrote this name wrong. It should actually be, it is a monophosphate, but it's also monohydrogen, which actually is very helpful. And so look here for a moment. We know the phosphate is 3-, so we want 3 of these total things added onto that. And yet we don't know if we want, say, 2 of these or 2 of these, and so the mono is going to help us figure out. So as we balance this, we're going to guess that we want 2 of those sodiums. We want 1 of that hydrogen from the mono, and then we have our phosphate, and that 3 charge is balanced by those other positive charges there. So this is our answer for number 1. For the second, looks like it's pretty simple. So lithium is going to be all the way over on one side of the periodic table with a charge of +1. And then selenium is going to be below oxygen and sulfur, and so typically come with a charge of -2. And so just to do some simple math, if we have 2 charges here and 1 there, we are going to need 2 lithiums to balance out that 1 selenium in this case. We'll see that math reappear again in our iron oxide example. We know that we want a 3+ charge balanced out by a 2, but we can't just have 1 or 2 of each of these, right? Because we need to get to sort of a lowest common denominator. One trick is that you have this many numbers, or 3 of the oxygens and 2 of the irons, and so we'll see if that balances out. Fe2O3. Here we have essentially 3+ times 2 is 6+, and then on the other side we have 3 times 2- is 6-. And so we can begin to see that these cancel out, and we have our equation, or I should say our formula for the iron 2 oxide. Again, one of the components of rust, for example. And so last but not least, we look at the components modifier, right? So penta referring to 5, sort of like a pentagram or a pentagon. And so here we're going to have Sb, F5 in total for the compound that we want to work with. Okay. So these are just a couple of different examples. Feel free to go through Wikipedia and look at all the different compounds out there. Usually at the bottom of a certain element, they have lists of different compounds. You can begin to practice with these as well. Feel free to stick to ones that you either recognize or maybe have heard of, or the ones that look really weird. That's always a good place to start as well. And so we're 2 questions left. We're going to do 284, which is going to be a balancing question. So here we're going to look at a combustion reaction, which I will write on the board. So 2C6H14 plus 19O2 is going to go to 12CO2 plus 14H2O. So a couple things. What is this equation detailing? Well, again, here we have a hydrocarbon. This is going to be something like a fuel. In this case, I think it's called hexanes or hexane. Hex again because of that 6. Here we just have good old oxygen. Again, even though it is a diatomic, right, we have 2 of those elements. We just call it oxygen, kind of like we call it just chlorine, even though it's Cl2. We have our waste product, the carbon dioxide, and we also have the water in this case, right? So you can see that this reaction, the combustion of really any fuel, is kind of a breaking up or redistribution of the carbon and the hydrogen back with that different oxygen. But that's actually not what this question's about. We want to know how many carbon, hydrogens, and oxygens are on each side, right? So let's do both, just for good measure, and then we'll feel confident. But you should imagine that if a reaction is balanced, which is to say that these numbers help sort of mediate or moderate the different components that we have, then it should be the same on each side, which is kind of nice. So let's start over here. It should be a little easier, right, because there isn't one element in both of the different compounds. So for carbon, we have 2 times the number of carbon that are in each. So we have 12 carbon total. And then we have 2 times the 14 hydrogen, which here will be 28. Lastly, the 19 times the 2 will be 38 of those oxygens in there. And so even though we already know that the numbers should be the same, let's see if the math adds up. And this is, again, going to be fundamental to chemistry, this balance of mass, and soon we'll find charge as well. And so if it doesn't balance, then, well, then you're doing magic, which is not part of this course. So we have 12 carbons from our first one and no carbons in the second. We have 28, right, or 14 times 2 in the hydrogen. And now you can get a flavor for how these problems will get more complex, right? We have oxygen in 2 different areas, and so we need to source that. So we have 12 times the 2 that are in here. That's going to be 24. And then hopefully, right, there's an extra 14, as we'll see in just a moment. And we can see we have 14 times that O, that 1 that we don't write. And so we can see here, it's really just a question of counting in that way. But soon I'll be having you guys actually balance reactions for yourself. And so you'll end up doing these checks at the end of each of them to determine whether or not you balanced correctly. And so for today, last but not least, we're going to have, what was it? Question 2124, or 124. It is in here somewhere. Okay, we have a list of different chemicals. And we'll see sort of how those do. So consider the following. We have chlorine. We have calcium oxide. I think that is known as quicklime. Really useful also for making concrete and cements and things like that. You have hydrogen bromide, which is about as toxic as you get. At least I wouldn't want to have to work with it. We have copper chloride. We have, oh gosh, there's always elements that I forget about. I think it is arsenic. Arsenic hydride, also probably very toxic. We have sodium nitrate, probably used as a preservative in some of those meats that you've eaten. And then lastly, we have nitrogen dioxide, or NO2, a component of some of those pollutants that are coming out of the back of your car. And so we're going to ask a couple questions about these different compounds, and I will circle them for each. So which of these are binary substances? Well, that is a very good question. Here we're looking at species that are composed of 2 different elements, at least in this case, right? Some of the others also have other elements in there, so not binary in that way. Which of them are triatomic? So that would mean 3 atoms. So we have, for example, copper chloride, and we also have nitrogen dioxide. In which do we only find electron sharing? So now we can see, for example, that we're talking about the difference between ionic, right? And when I think of ionic, I always think of sodium chloride. That's a plus. And then molecular. You can think of a lot of things, but I think of methane, for example, right? There's no distribution of charges. It's all just kind of one molecule in that way. And so, right, sodium, similarly, this is going to be ionic in nature. We also have copper being ionic in nature, hydrogen bromide, arguably even calcium oxide. This is neutral, right? So we don't actually see any ionicity in that way. And so in terms of only having molecular electron sharing, I would say that we have our arsenic compound, kind of similar to the CH4, right? And then here we actually have not only ionics, but the NO3 is molecular as well. And thus the question asked only molecular, and so it is not NO3, at least not yet. Which are diatomic. So these are going to be referring to the 2 different atoms. So I guess binary are going to be our Cl2, and then our diatomic are going to be these 2 species here. In which molecules do we only find attractions by ions, so not molecular in this case? So we're going to have definitely in the H plus and Br minus, definitely in the Cu2 plus 2Cl minus, definitely in, well, not only ionic, right? This has both. And then this is going to be molecular as well. And so in this case now we can classify, I'll put a big I next to it, so we have ionic compounds. This is ionic, though it also has molecular features. This is going to be ionic as well. And then we're going to have molecular. This, I would argue, is ionic, even though it kind of can be seen as molecular. And then we'll leave this out, but I would guess you consider this molecular as well. Okay. So that's going to be our sort of quick review of some examples and questions in Chapter 2. If you're having any problems with these, feel free to come to me. Otherwise, I will see you all in class and torture you there. Good luck on the next exam. And again, if you were unhappy with your first exam grade, please come to me earlier than later, and I'll give you lots of good problems to do.